when I say it goes down, right, there's actually only really two ways to draw a Newman projection from the front. Okay, the backside can be different, but when you're looking straight on it, there's only two ways to draw it. One is going to be like this. Hey, this is for later. I made 14 copies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
You can have mine if you want.
No, I have this one. But maybe there's one's. They think they shorted me. That's okay. So, anyways, you could draw it two ways. You can draw it like that, and you can draw it like that. That's the front. All right. You see the only difference, right? In one, the center one's going up, and the other one's the center one's going down. Which one do you think I'm going to use for drawing that one? The one where this is going down, right? So like that. That's what you're drawing. The other way to draw it is flipped over like that. If you had it like this, if the drawing was going like this, that is if it was going, so this, oh shoots, I don't know what I just did. Just disappeared everything. This one goes here. But if I were to draw the zigzag like this, then you'd be looking at it along this bond axis. And so you would use that. Makes sense? Basically, there's two ways. And here's the thing. For staggered, so this is how you do the staggereds, okay? You determine which way the one in front of you is like looking at you, either it's going up or down, and then the ones in the back for staggered are always in-betweens. So these are the ones in the back. They go like this. And for this one, they'll go like that. Okay. So we're going to draw a Newman projection for this. Okay. And we decided that we're going to draw it on this one. So now I have to fill in the blanks. Because basically, when I drew that part, I didn't put hydrogens, I didn't put carbons. It's just blanks, okay? So what's this group, right? It's the CH3. So that's going to be, bless you, CH3. So where's it good? Mentally, got the picture? Where is this group?
All the way
on the top. It's this one in the back. And then everything else is hydrogens. So figure out what's on the bottom, what's on the top, or left or right, the big groups, and then draw the hydrogens in. So leave the hydrogens for last, and now the rest of them are hydrogens, and you can just pop those in here. Now, you don't see those on here, but remember, this is a CH2, and this is a CH2. Like that. So this is anti. Oh, sorry, I forgot to draw CH3 up here. This is anti. It's the lowest energy. So now what I want to do is draw a gauche, right? So now I have this. I need to draw a gauche. So this is anti. Right. Now I'm going to draw a gauche. So remember, it's a there's only two staggered positions. It's anti for butane and gauche, which is gauche this way or gauche this way. Okay.
Isn't it when they're on the same?
It's both gauche.
Okay.
Gauche. Good. Got it? Okay. Sorry. That was a little overkill. But I haven't had my coffee. Got to do something to stay awake. I have a puppy. That's all I'm going to say.
Uh-huh.
Super cute. Did I tell you I had a puppy?
Yeah, so much problems with puppies though, all the time.
Oh, no. I've already trained her to sit and take food from me.
Yeah, I took mine.
I want to hear it. So, off task. We'll talk about it later. Because I got to run home after this. Take care of the puppy. It's my daughter's dog, by the way. It's mine. Okay, so I'm going to draw this one. Okay. Well, actually, let me draw this one. Sorry, I want to draw like that. So, what do I do? Circle, right? And then, which way is this one going? It's going up, right? This, 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 and this. All right? This is a CH3. Where's the other CH3? on the right. It's on my left, but yeah, I get it. And then the rest are hydrogens. Okay? Okay, so I kind of lied. There really are 4 ways. Okay, not really, I guess. It's really on 2 ways. I guess my brain wants to call it 4. Yeah, we'll leave it at 2. It'll work. It always works. All right, so then let's see. Now we're going to have to do eclipse. These are all the stackers. There's 2 gauches, there's 1 anti, and now we're going to do an eclipse. So to do eclipsed, I am going to erase this whole darn thing. Oh, shoot. I've been scribbling with my fat finger. There we go. So to do an eclipse is a little tricky, okay? So I'm going to do this. Now this is still butane. And this is the worst of the eclipse because the big groups are close to each other. The closer the big groups are, the worse it is. So it's going to be, that's how it looks. It's straight on. But you can't draw it straight on like this. Like if you drew that and you put it on paper, you'd be like, I can't tell which way things are going, right? But again, look at the front. And which way is this one going? It's going up, right? So the one in front of you, this one goes up. And then it goes down and down. So that's the front. Now, the back, what you have to do is you have to decide, do you want it to be left or right? It doesn't matter if it's left or right. You just draw the other sticks next to it, like this. Oh yeah, that was really bad at art. It's supposed to be kind of projecting from the center. So it doesn't matter if that's left or right. And the 2 CH3s are close to each other, right? So you go CH3, CH3, and then everything else is just H's like that. All right? That's eclipsed. 0, they often say eclipsed 0 because it's a 0-degree angle between the large groups. If it was eclipsed 120, this is 120 degrees, like that. So if you want to draw eclipsed 120, what you have to do is you go like this. Oops, sorry. Okay, now we have, this is harder. But you can only do this with a model, right? Which way is the methyl group? All right. There's a group going up like this, right? So I'm going to do this still. But where's the methyl group? Oh, it's this one, right? Sorry. No. I'm just drawing this like this so that you can get the orientation. You see the hydrogen that's going up? So that's the orientation. So this one's on the left. It's like an aerobics instructor. That's my right. It's weird. Okay, left, CH3. And then this one is, oops, supposed to be like this. All right, do that. It's not staying. It's up, right? So then what you do is you go like this. You draw your sticks. And then in the back stick, you put a CH3 like that. So that's eclipsed. 120. So this is eclipsed. This is eclipsed. And then the hydrogens are like this. This one is often known as 0, and this is 120, like that. In terms of energy, it's high in energy, but it's not as high as the 0-degree one. The 0-degree is the highest energy one. All right. Cycloalkanes. And we're going to do the most work with cyclohexane. But a cycloalkane is just an alkane, no double bonds, in a ring. So that's where the cyclo term comes from, okay? The high, so now here's the thing. You take your cyclohexane and you're going to break one of your bonds, okay? And you're going to try to make a cyclobutane out of it. Try to. You guys do too. What do you feel when you do that?
The force of not wanting it to
It does, yeah, it does not want to go together. You have to force it to go together. All right? If you can do a pentane, but it's a little hard to get a pentane, so you got to sort of bend it a little bit, and you can like stick it together. And then if you try to put a cyclohexane together, it just kind of goes together. Just kind of does. right? And that's an indication of how much strain there is in the molecule, because when you form a cyclopropane or a cyclobutane, the molecule will have a lot of strain, and that will cause it to break apart much easier because it has that strain. So we call this strain angle strain. I'll get it back to cyclohexane here for you. Right, I think did I screw up my orientations?
You killed it.
I killed my orientations. Let me make sure. Yeah, I did. Look at that. That's cool. That's a geometry problem. I got to fix it over here, though. Okay, I'm good. So we talk about angle strain, and that applies only to the ring. They also have some twisting, torsional strain, and they also have some steric strain. So again, steric strain is the pressure of the big groups on each other. Like too close together, their electrons repel. Torsional strain is the twisting of the molecule. It wants to untwist from that torsion, that steric strain. So butane has a lot of torsional strain in it because these big groups, right? If they're next to each other, there's a lot of torsional strain. If they're apart from each other, the torsional strain is very low because it doesn't want to twist out. This is the lowest energy configuration. So when you're here, it wants to twist around and get to here. That's what gives it the torsional strain. Okay. Let's see. Oh yeah, I have a small view on. Okay. Cyclopentane, when it forms, it kind of looks like an envelope. If you think about cyclopentane, right here's C's like this. And so when it sits naturally, it sits like an envelope. So they called that the like envelope for pentane. I don't know, it's weird, but so we'll go on from there. Okay. So the ring that was easiest to close is supposed to be cyclohexane. If you're not familiar with doing that kind of stuff, and the one with the smallest angle strain would then be cyclohexane. It turns out as you get bigger, well, let me ask this question. Why is it that is the way it is? Why is cyclohexane give you the lowest angle strain?
There's more room for it to...
It's not the more room, because it turns out angle strain goes up as you go to 7, 8, 9, 10.
It just feels like it doesn't have, like it can't reach.
Yeah, they can't reach, but this one reaches easily,
yeah,
right?
That one does.
But why does it reach easily? Anybody got an idea?
I don't know how to put it into words.
Is they're exactly opposite of each other?
No, not exactly. What's the angle that these like to be at?
120?
No? 109. Because it's got 4 groups on it, 109.5. Turns out in cyclohexane, when it sits like this, they're all at exactly 109.5 or very close to it. So that's why there's little strain. If you put it in a cyclopentane, this angle has to change, and it causes the strain in the molecule. It has to do with the Vesper theory stuff that you learned before. Okay. So we're going to have to draw cyclohexane. I sort of did it visually. I'll try to explain to you what I did. You can draw cyclohexane, but we want to be able to draw the conformers of cyclohexane, like the different positions that things are in. And we've established some rules for what those things look like. So on paper, if you're not worried about conformers, that's cyclohexane. You should just get a piece of paper and draw that like 1,000 times. Yeah, and then eat the paper. But that's only if you're trying to keep it a secret. You want to tell the world. And then you get spray paint. Never mind. That would be funny if I started seeing cyclohexanes everywhere. But I'd be like, oh my God. All right, City College, what happened? So this is cyclohexane. Okay, now maybe you don't like drawing it sideways. Maybe you're not comfortable. You can also draw it like this. But for the purposes of what we're doing today, I want you to draw it so the points are at the ends like this. Okay, and then you're going to think about it like that's this flat. You're looking at it like that, two-dimensionally, right? And then what you're going to do is you're going to tilt it towards yourself. So what happens when you're looking at it in two dimensions, the space is really big, right? And then when you tilt it, and it's tilted towards you, what happens to the vertical space here? It gets smaller, right? So basically you're going to draw cyclohexane, and then you're going to just draw a distorted version, just like this. So you squeeze it like that. And then what are these groups? That one's going up, right? This one's going down. So what you do is you draw it like this. And then like, that's kind of a bad one. I better draw it a little bit more dramatically or you won't see it. Like that. Pick a point above the line, right? And draw to it. And then pick a point about the same distance below the line. And then draw to it like that. This is known as chair. Because it kind of looks like a chair that you could sit in with spikes all over it. But yeah, it's chair. Called chair. And then this, so see that's chair. This is called boat. Because it looks like a little boat with little flagpoles at the top, you know? And the little prow, the mermaid, and the whatever, the place where everybody goes to the bathroom on the end. That's what they did in the old boats. They just had a thing at the end, and you sat off the end of the boat.
The boat part.
I learned about that when I went to visit Sweden one time. They have a big warship there called the Vasa. They pulled it out of the river, and it was still intact.
Have you ever been to Scotland?
Huh?
Scotland.
Been to Scotland.
Oh, is it pretty?
So.
No.
Thank you.
Is the Netherlands?
Okay, so now I'm going to draw a boat. So for boat, you do the same thing. Okay. You got to cheat a little bit and make the end, like one end longer here and one end longer here. So the bottom line's a little bigger. That's the one that's towards you, right? And then you pick a point above like that, and then you draw it to the top like that. So that's how you do that, okay? So again, one, it's like origami instructions. Draw two parallel lines. You could tilt the parallel lines, like when you decide you're super fancy, you can tilt the parallel lines and it looks cooler that way or something. But see, like they did here, they tilted the parallel lines. I didn't do that. But if you want to, then you have to think about drawing it like that. And then once you do that, you pick either a point above or a point above and a point below. And then you draw to the point. Okay. That's the way to think about what you're doing systematically. And then after a while, you just go, blah, 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 and they just come out of your fingers like magic. Right, so I'm going to draw another one of these. I'm going to draw big. Because what I want to do is I want to show you this, how you draw all these groups on there. Okay? Ooh, not doing that yet. I'm going to make a blank slide.
What did they call that one? The one that looks like a cat.
Like a cat?
With the ears.
I don't know. Oh, boat.
Yeah.
All right. So here we go. We're going to draw chair. And I am going to put the right side down. So first thing I'm going to do is I'm going to draw two parallel lines. I actually offset them a little bit sometimes, like that. I pick a point above and I pick a point below, like that. And I try to pick that point high enough up that there's a pronounced angle, otherwise it looks weird. So I'm going to do that. I'm going to pick that, like that. So now I have the right side down. So what that means is, and so check this out, this freaks people out when you do this. This is one of the conformers of cyclohexane. So make this, you have it in front of you, make it do this. You have it in front of you, make it do it. Make it do this. And then if I turn around, you see how it's not the right way now? I want you to take this side and pull it down. And now it's like a capsized boat, because the points are going down. You take this side and flip it up. And now it's in chair again. And now it's in that orientation. All right. So these are fun to play with because you can just sort of twist them and they do sort of cool things. So do that a couple of times. And tell me what's happening to the hydrogens. Like when you do this. Just observe one, like the one that's closest to you. Or the two that, the pair that is closest to you.
They're moving away from the other hydrogens.
Yeah, they're like chasing each other, right? One's trying to chase the other and pushing it down, and one, when you come back, it pushes it back up. Now, you notice, like, what happens when I do this. I'm just sticking behind you guys because it's a little hard to see from all the way back because this room is horrible. But if the legs were all the same length, I don't have to leave them all the same length. I couldn't get the same length once. I should have done it on yellow. All right, when you do that, it'll stand on 3 feet. And then these guys, you see these ones? They're going straight up. These ones are going straight down, and it's every other. So these are known, these ones that are going straight up are called the axial. So what we're going to do is we're going to draw that onto our drawing. Okay, so which ones go straight up and down? Which ones go straight up and down? Okay. The one like on this point goes up and down, right? But it's going down like this. And then this one's going up. See that? In the drawing? I think you see it in the drawing. It's not perfectly straight, but it's flimsy.
I was like, what are we looking at? But it's behind me.
Yeah. So this is actually what it looks like. Every other one is going up or down. You guys see that? There's my up and down, up and down, up and down.
It looks like someone's body when they're stretching.
So those ones are known as axial. And what are the other ones doing? So I have the ones going up and down, and then they have the other ones going which way? Look, no, look, they're not going straight up and down. Look at the model. They're at angles, right? So they're kind of going like this. If you were drawing it, and I'll tell you sort of the geometric relationship as you draw these. But it's kind of going like that. Those are, oh, and this one has one going over here. Sorry, like that. Oops, I should draw like this. The ones that are going vertically, and let me try, I'll draw them in a different color too. I don't know. That looks like an interesting color. Those are known as equatorial.
They're equal?
Equatorial because they're on the equator.
Yeah.
And they're pointing out like the equator. Equatorial. So you're going to have to be able to draw this, right? So you'll have to practice doing that. It takes a little bit of practice getting used to where things are. You know what? I think I will leave the Newman projections for cycloalkanes for another time, but I do want to talk about strain and cyclohexane. So let me grab my methyl groups here. I'm going to take my butane apart. do something here. You're going to have to tell me which has the most strain in it. Okay? And so I'm going to build a couple of these. So I'm going to make it 1, 3, and they're going to be cis. Okay, now cis means on the same side. I'll make 1, 3, cis. So I can go like this. And this is dimethyl cyclohexane. This is 1, 3. You can go 1, 2, 3. Right? So does this have high strain? Or you have to tell me, I'm going to do this. I'm going to flip the ring. It's called flipping the ring. I know it sounds obscene. Which has more strain in it? The first one, why? The big groups are closer together. So it turns out if you were to draw this structure, the way you draw it in the most stable for 1, 3 cis is to put these right in the equatorial position. So now what we'll do is we'll do this. I'm going to do 1, 4. Okay. And I'll make it cis, just for fun. Now what does cis mean? Right, same side. Now it doesn't quite look like they're on the same side, right? But they are both on the top side of the carbon they're attached to. So there's 1, 4. Right, and this is one way. I'll flip it like this. Does one of them have more strain than the other, and how would you figure that out? So look at what you have, and look at what this methyl group is the one you worry about, because it's axial and it's close to everything. What is it close to? What is it closest to? Like what's here? Hydrogens, right? And it's close to 2 of them, right? If I flip it, how many is this one close to now? 2. So it's the same. Stability-wise, these two are the same. Okay. Now, if I do, you know, I can make them trans as well. I can stick this one on here, and you'll see it's the same kind of thing. But okay, I have that right, and I'm going to flip it, and then you tell me. Wait, I had it. I broke it. So there's that. Both big groups are equatorial, right? So now I need to flip it, and I'm going to go like this. Which one is more stable? This one? It's like I got the better one. Better 2, right? Because they're both equatorial and away, and here they're both axial and close. This one is close to the hydrogens at the bottom at the same time as that one. All right, so now let's play this mind game, right? Which is, I did it here, right? If I make it cis again, so now this is going to be harder to see, so I just try to burn that into your brain, right? There's 2 interactions at the bottom, 2 interactions at the top. I can switch it like this. How many interactions are there that I worry about? 1. Well, it's this one with these 2, right? So these 2. So this one has 2 interactions with the hydrogens, and they're steric. This one's because they're pushing on each other. The other one had 4, and then the equatorial, and none. So all 3 of those are different in energy, right? Cis, trans, right? And depending on which way the boat is flipped. So you're going to have to, it's going to be a little difficult, but you'll have to be able to draw these and then look to tell which groups are closest. The thing you have to remember, and this is what saved me and will save you, is axial's bad. Right? Then the more axial interactions you have, the badder you are. The worse you are. I grew up in Reedley. That's what I blame my language skills on. We went to Alta Elementary, out in the country, no supervision. It was awesome. Okay. Well, I had supervision at the school, but at home, different story. Okay, I think that's all I'm going to cover. That means we'll skip the stuff on the Newman projections of the cyclohexane. I don't remember if I put those homework questions in there or not. I'll look at it later and we'll post that. Let's talk a little bit about alkenes and get as far through alkenes as we can. So all of this homework is due except for Newman projections of cyclohexane, if there's any in there. I don't even know if there's any in there.
The alkenes are the ones that are unsaturated.
Yeah, let's talk about that. Discard that. Let me open that. So we'll get as far as through this as we can. It's actually a very short chapter. The most of it focuses on structure and nomenclature. Okay, so we'll talk a little bit about structure. You kind of already know a little bit about structure of the double bonds because we covered that in the first chapter. So, yeah. So what is an alkene? An alkene is something that has a double bond in it. Right? So C's. Ooh, weird color again. I'll get back to purple. It has C's, H's, right, and a double bond. So the key is, though, that it has double bonds, and then we'll call it an alkene. Okay. And there'll be some nomenclature rules. So let's go ahead and just get started. The structure of an alkene, like ethylene, for example. This is CH2CH2. This is ethylene. These all are, except for limonene, actually. Limonene is the lemon citrusy smell, right? That comes out of citrus. Limonene is also an alkene, but it has two double bonds in it, so it's actually technically known as a diene because it has two double bonds. There's a joke there, but it was dying.
Yeah, it was
I've been dying to say this all semester. Okay, there's all those jokes in there. So there's ethylene. You draw it as CH2CH2. It has a double bond here and two hydrogens like this. So line drawing looks like this. You could put the hydrogens if it makes you happy. Okay. We say that it's unsaturated. Why do we call it unsaturated? Because you can put more hydrogens. It has fewer hydrogens than the alkane. If you can put hydrogens on it, it's unsaturated. If you can't put hydrogens on it, it's saturated. Okay? Unsaturated because it can absorb, that's what we would say, more H's. So that's what saturation refers to. It's like saturated fats. They can't absorb any more hydrogen, and it's their structure that makes them bad for you. And unsaturated fats, there's what we're about to talk about, are very rigid and don't like solidify as easy, and so tend to be better for you. Okay, something about a double bond that we need to sort of get out of the way is that the double bond is made up of a sigma bond here between, this is sp2, and p orbitals. And this is known as the pi bond. The interior bond is known as a sigma bond. Okay? So we have pi bonds and sigma bonds. It's the presence of the pi bond in the double bond that keeps it from rotating. If you try to rotate the pi bond, you have to break it to rotate it. So the way I demonstrated this before is I think I danced with somebody, right? And if I don't let go of one hand, they can't spin unless we both spin together. So on a relative basis, right, this molecule can spin, but only if the pi bond is broken, that can it spin, okay? Right. So the fact that it can't like spin means that you can have something called cis and trans isomers. So for cycloalkanes, we had cis and trans. Right? Cis means on the same side, trans means on opposite sides. It's the same thing for alkenes. Okay, so in an alkene, this is an example of cis 2-butene. I'll just give you the name. We'll go over the rules for naming it though. It's cis because, and this you got to get used to doing this. If you draw a line through the double bond like that, you look to see where the big groups are, and that's normally what's called cis. Okay, so that's cis 2-butene. If I draw a line down this way, all right, that's trans 2-butene. So here's what happens though. Cis 2-butene and trans 2-butene have different stabilities. Which do you think is more stable? And give me a reason why. Trans, why?
Big groups are on opposite
Big groups are far. This is like a general thing you're going to see. Big groups far away, better. Better, not necessarily better, but more stable. I like to call it better because I think more stable is better, but did I say I grew up in Reedley? Okay, so if you take cis 2-butene and you expose it to light, I don't know if I can get this to work. I need 2 of these. So you can actually think of a double bond as being like this. Kind of a misrepresentation, but it kind of works too. All right. I have a sigma bond and a pi bond. So I have these 2 bonds like this. And then I put 2 groups on either end. Like this. That's cis 2-butene. But they don't like each other, right? Because we don't think about how big these groups are, but they're pretty big. If you break it, right, ready for this? It can go like that, and then it can reform. Now, because of the way geometry works on these things, you can't just do that because they're not exactly sigma and pi bonds, but yeah. Once you break one of the bonds, it can rotate, and then the other bond will form back once it basically cools down or loses the energy. Okay? So one of the ways that this is done is by exposing it to light. And when you expose it to light, you break the pi bond. It's the weaker of the 2 bonds. And the molecule will rotate on the sigma bond, and then the pi bond reforms, and it'll be like this. The majority of it will be at this conformation. Now, if you take trans, just pure trans 2-butene, and you expose it to light, you'll get a little bit of cis 2-butene, because in those rotations, when it loses the energy randomly, some of the times it'll be in the cis configuration. Okay? And I think I mentioned the rotation rate on these things is about 1,000,000 times a second when they can freely rotate. And so as soon as it loses the energy, just whatever configuration it's in, it freezes. Okay, we practice cis and trans. So we'll call this A, B, and C. I always forget to add letters, so I'll make it easier. A, B, and C. What is A? Trans. And I'm going to also call it E, and I'll show you why in a second. There's another nomenclature system that's a little bit more complete. What's B? Cis. Right? Big group, big group. Big group, big group. Cis. What's C?
Or cis. The hydrogen bonds are close to each other, but then there's no big groups.
If you flip it, what does it become? Same thing, right? It doesn't have cis or trans. So moral of the story is sometimes I lie to you. There's 3 options. If the 2 groups are the same, can't be cis or trans. Because the big groups have to be apart from each other. But the groups are the same, they're always going to be the same, right? So no cis, no trans. So neither use a good word. Cis or trans. The word I want you to get in your head, or the letter I want you to get in your head for cis is Z. Okay? And I'll show you why that is in a second, but they're related to each other. Okay, so we do this thing, it's called EZ nomenclature. So the E and the Z. And the E stands for entgegen, it's German, of course. It means opposite. And Z is for zusammen, which means together. Right? So, yeah, zusammen is simple. Yeah, I always think the more we get zusammen, the more we get zusammen, the happier we will be. You know that song from childhood? The more we get together. The more we get together, so zusammen, together. So I sing that song and it reminds me of something. All right, so this one, right? This is, oh, sorry. Dang it, I keep touching the screen. It keeps jumping. This one, this first one, we'll call this A, and this one B, right? If we're looking at structure A, you notice I have a CH3 and a Cl on one side, right? And we talked about big groups being on the same side or big groups being on opposite side. And this one, now I have two big groups. And so how are we going to define big, right? And it goes by atomic number. So if you think about atomic number and you think about the, it's not strictly the mass, but the mass of the atom that's attached. That's what we're using. Okay, so what's heavier, Cl or C? Cl, but it's, you know, and we're really going by atomic number. It's 17 versus 6. So when we're talking about whether or not the big groups are together or apart, we're looking at atomic number now. Okay. So this one and this one are together, and when we use that nomenclature, when we use the atomic numbers to do it, it's called zusammen, Z for being together. Okay, what about this one? I'm comparing now. I have a CH3 and an H, right? And here I have a CH2CH3 and a Br. Like physically, CH2CH3 is bigger, but by atomic numbers, we're only looking at this atomic number. So the Br is bigger, right? So this group is opposite of this group. And so we would say that is E. This one is Z. All right. Now we'll practice some nomenclature. And I'll tell you what the actual, this rule about the atomic numbers is called CIP notation or designation. It's the first letters of three different guys' last names. This guy named Kahn, Ingold, and Prelog, and then nobody remembers them, but they remember CIP. Right? If two groups on one atom are the same, right, then it's neither cis or trans. So if I have two hydrogens or something like that. But priority is based on atomic number. Now, what if the atomic number is the same? Like it's two carbons. Like you see this a lot, right? And in alkenes in organic chemistry, let's say I drew this CH3, then sorry, let's do this actually. CH2, C, and then I'll put a CH3 here and a double bond, and then a C, and let's do a Br and an H like that. Just because. So remember I said you based it on atomic numbers. Well, the right side's easy, right? The right side, the Br, this is the high priority group. We assign a priority to it. Which one's higher priority on the left?
CH3, CH2.
Yeah, because even though there's a carbon like this and a carbon like that, right? What's different about that lower carbon? It's attached to another carbon, right? So what you do is you look at that next carbon and you say, oh, well, this carbon on the bottom is attached to that carbon, right? This carbon is only attached to hydrogens, and so that's how it wins priority. Okay. You look at, if it's a tie, you look at the next atom. And the first time you see a difference, that breaks the tie.
Can-
Move my head.
Yeah.
Yeah, sorry.
I'll just.
I'm going to change slides now. Forget.
Okay.
Okay. Let's do, let's see. How's this thing organized? Oh, easy practice. Get it? Easy. Okay. Again, A, B, and C. And then we're going to do some nomenclature. A, B, and C. So for A, do I assign easy to that? Because there's two double bonds. No, because what's this N group actually? CH2, right? Remember, carbon can have 4 bonds, so if you see a double bond on it, it has 2 hydrogens. So this is a CH2. Has 2 of the same, so you don't assign priorities. You don't give it an easy designation. For this one, right? Do I do it with that one?
Yes. Wait, no.
No.
Why no?
Because it's similar to the one before.
Yeah, this one has 2 methyl groups on it, right? So it doesn't have to be just hydrogens. People get in their head it's just hydrogen. If you have 2 of anything that's the same, then there's no designation of EZ. So that one's a pass. You don't have to assign E or Z to it. You'll just name it, and you don't have to use the EZ designation. Okay, so B. So I'm going to draw a line like this, right? And so for the left side, let's just look at this side. Which one's higher priority, the Cl or the Br with the CH2? A lot of people want to say Br with the CH2, right?
No.
But it's the first time you break. So here, this is 17, right? But it's first thing that's attached is this. You look at you don't look at the whole thing. You just look at where it's attached. So it's sure the Br is like 35, but this is 6. So it's not just. Remember, I said it's not really the weight; it's the atomic number. But it's the first time you see a difference in atomic number going away from that atom. So if I'm going away from this atom, like this way, first thing I see is 6, and then I see 35 is over here. But this is the one that matters because that's where you break the tie. Okay? Let's do the other side. It's a little tricky.
The oxygen.
Is it the double bonded oxygen or the single bonded
The
oxygen?
double bond.
Double bonded. Why do you think that is?
Because the atomic number for the oxygen is bigger than the one that's attached to an H.
Yeah, so this atomic number is 6, right? Or 6? Yeah, 6. No, it's 8. Well, this one's 8 too, right?
You added.
But it's attached twice. So it's like it's attached to 2 oxygens. So if you think about it, this one is bonded to, this carbon is bonded to an oh, I can't see it there. Can you see it? No, you can't see it there. This one is, this carbon has an oxygen, and then a hydrogen attached to it, right? I sort of list out what it's attached to. And this one is an oxygen, right? It's a carbon bonded to an oxygen, and then it's bonded to 2 hydrogens. So because this top one has 2 attachments to the oxygen, it wins at this point here when you're looking at the comparisons. It has more oxygen attached to it, even though it's just one. It's attached twice. Okay? So now we're going to go over nomenclature, okay? And we're going to use EZ rules. Talk a little bit about stability too. And that's about half or 2/3 of the chapter actually. Okay, nomenclature rules, okay? The alkene functional group has priority over alkyl in halo. I won't mix alkenes with alcohols right now because I know it sounds weird, but too many rules. You don't need those yet. You'll need maybe later. So because it has priority in the parent chain, right? Lowest number in the parent chain. And the rules are the same as that for alkanes, except the double bond has to be part of the parent chain. So the double bond has to be included in the longest chain, which leads to some weird things, but you'll see how it works. Double bond gets the lowest number. You have to use cis or trans for except in rings that are smaller than 7, or 7 or smaller. As soon as you get to 8, then you have to say cis or trans. Because in a ring, if you have a double bond, right, like, it can only be cis, it can't be trans, because you, like, think about how to, like, right, the strain that would cause to have to twist that to get to form. So it has to be cis in a ring. And here's the other weird things. When you number the double bonds, right, you have to have the numbers increase across the double bond. The numbers have to increase across. So I'll show you what that means here in a second, okay? I'll show you on the first one, actually. So I forgot to put 8 letters. I got the boxes for the letters. That's an improvement. I'm going to call this A, and let's call this B. Okay, so if A is not an alkene, it's an alkane, right? And so if I was going to give me the parent chain number. Identify the parent chain. 6. All right, 1, 2, 3, 4, 5, 6, and I would number from the left because that gives it a 3 instead of a 4. Okay? Now, for the alkene, it looks very similar, right? But here's the trick. The double bond has to be part of the parent chain. And the numbers have to go through the double bond, have to increase through the double bond.
So it would be 5.
It's, 1, 2, 3, 4, 5. And then the alkyl part, the little ethyl group, that's a substituent now.
We don't count.
Well, you have to put it in the name. We're going to give it a name now. So this is the parent, okay, is 5. I put a little space there because I'm going to add a number to it. It's pentene. You change the E to an ENE, or basically just add NE to it. Or sorry, the ANE, you convert to an ENE. And then you have to say where it is, and it's on the number 1 carbon. And then it's assumed that you put the number on one side, 1, and the number on the other side's 2. So when you say, 1 pentene, it's just not on the 1 carbon, it's between 1 and 2. If it was on the 2 carbon, it's between 2 and 3. Okay. This substituent is an ethyl group. And what number is it on? 2. By the way, get flashcards, because like a third of the test will probably be nomenclature, right? And just all the numbers, have them on flashcards, and then just have some structures from the lecture that you have to practice naming, and just go through them, and then get some problems from your book. So 2 ethyl, 1 pentene. Okay. Again, having to number through the double bond makes a difference.
I got a question. So we started with 1 at the top. Is it because we wanted to give the ethyl group the smallest number, or does the double bond have to start with
The
smallest
double
number?
bond is the smallest number.
Okay.
And we numbered it from there because if we tried to include the ethyl and get the longest chain without the double bond, you could have, but then that you didn't give the alkene priority. You give it the lowest number.
Yeah, but what I meant, so if the ethyl was on the 4 carbon, we would still number it the same way.
Yeah.
Okay.
Yeah.
I see.
So, sort of like here. Again, tell me what the parent is on the left. For A, that's the alkane. And B, that's the alkene. What's the parent number? And which way do I start the numbering from, left or right? Left, right, and it's left, correct? Sorry. And the number is 5, right? So 1, 2, 3, 4, 5. So I have a double bond in the middle-ish. Double bond takes priority. There are 2 ways to number this, okay? I can go like this, 1, 2, 3, 4, 5, or I could go 1, 2, 3, 4, 5. Which gives the alkene the lowest number? 2, right? It's going from right to left. And so that there's a methyl that would be a 2 and an alkene that would be 2. The alkene takes priority, and you just ignore the alkyl in the halo groups. Well, as far as numbering goes. So this one becomes 2-pentene. And it's 4-methyl. And it has a line through it like that, and the groups are different. Right? The last one I didn't do that because the alkene was at the end. I didn't need a cis or trans. I'll go back to and show you that. So, cis trans, what is it? Trans is opposite, cis is on the same side. Trans. If you're thinking about, again, let me clear this out. I'll go back to that. If I draw a line like that, I'm looking at this group versus this group. And they're on opposite sides of that line, right? And so it's trans. Don't forget, there's hydrogens here. You're going to have to come to accept that there's hydrogens, right?
And if the double bond is not at the end, is when we have to...
Then you have to, yeah. Well, unless, I mean, it could be in the middle and have methyl groups on one end or ethyl groups that are the same. So like this one here, I didn't do that because right here I have 2 hydrogens. Oh, sorry. At this point here, right, I have 2 hydrogens. So when I draw a line down it like this, all right, you have to think of it having a hydrogen here and a hydrogen here. Like these two, this is the big group, right? But the top, the 2 hydrogens, doesn't matter. So we don't do cis or trans. Oh, so how would I name this cycloalkane? Not the alkene, but the cycloalkane. Okay. It's a cyclo what?
Hexane.
Cyclohexane. And I have bromo and I have methyl. And this is one of those weird instances that you sort of have to pay attention to, like the alphabetization when you give numbers. I could go 1 or 2, right? Or I could go 1 or 2. Bromines and methyl groups are like siblings in an ideal parent world. Neither one has priority, so you just alphabetize them. Okay? When you try to make it fair, you can just do them alphabetical order or reverse alphabet, or you just randomize. Right?
1 bromo.
So we're just gonna, yeah, so it's gonna be 1 bromo. The numbering is decided by Burr. So it's 1 bromo, 2 methyl. And then cyclohexane. Uh-oh. I'll finish lecturing here a little bit because my money's about to run out on my meter. I'm going to lock the door, run out, and move my car. Puppies. I'd bring the puppy. She's so cute. Oh my gosh.
Bring her out
It's
one
not
of
my
them.
dog. That's my daughter's. So
I wanna see
I can't. Not allowed. So I'm going to number this one. Which way do I number this one, right? This one, the alkene gets the priority. So I'm going to go 1, 2, and I'm going to number across it, right? And 3. Because if I go the other way, if I go from the 1, 2, 3, 4, 5, that next substituent gets the 5. So you choose in a ring so that the substituent that's not the alkene gets the lowest number. It leads to some weird stuff. So this would be 3 bromo. I'm just going to name it. 4 methyl. 1 cyclohexene.
Why is it 4 methyl? You put a 5.
So let's summarize real quick what's going to be on the quiz through nomenclature, all the nomenclature, and then the rest of it will go on the next one. But they're all going to be worth the same. So, and I will have to lecture after the quiz on
What are
Tuesday.
you writing? Do you have a quiz on Tuesday?
Huh?
You have a quiz on Tuesday?
Every other Tuesday,
The other two.
This is fantastic.
which is great because otherwise they get there's a lot of material. So digest as much as you can. There's no Super Bowl this weekend. All that stuff. So it's great.
My beautiful team won, so I was happy.
I'm going to draw one up here for you to consider.
Don't even root for your own state team.
That's not my team. Sorry.
Think about that one. Which way would you number it?
My
The
beautiful
two
team
in carbon.
has been my team
You
since
know, the methyl.
1999 when I started.
Right? Because you want to do this 1, 2,
The other one, one more.
1, 2.
Yes.
The first non-alkene substituent gets the lowest possible number. 1, 2. And then this gets to be 6. Because it's on the double bond and there's only one of them, you have to give it the lowest number, and then you have to count across the double bond. The lowest number is 1. All right.